Hello everyone and welcome to this first lecture in data-driven methods for dynamic systems. Now the goal of this lecture today is to really introduce one of the most powerful tools from linear algebra that we will carry through this lecture series, at least for the first few lectures. And what we're going to talk about today is what's called the singular value decomposition. Now, this is one of many different methods for factoring a matrix, right? So when we think about factoring things, we typically think about factoring numbers. 6 is equal to 2 times 3. We have the prime number theorem that tells us that we can uniquely factor integers. Now, with matrices, this isn't the case. There are many different ways of factoring matrices, and it depends on your application. We have things like QR and LU decomposition. We have diagonalization for symmetric matrices, or at least matrices that have a full geometric and algebraic multiplicity for their eigenvalues. But what I want to talk about is one that's sometimes not taught in an introductory linear algebra class, but has become a weapon of choice for data analysts. And that, as I mentioned, is the singular value decomposition. Now, if I'm given a matrix A, in this case, it could have any size. Let's say it is a capital N by capital N matrix. Now, the first thing that you should immediately notice about this is that it is different than a lot of the traditional settings where for matrices that you work with, where you often have to have a square matrix. In this case, this could be a rectangular matrix of any dimension. And what the singular value decomposition does, the SVD, well, what it does is it takes that matrix and it writes it in the following form. It writes it as a matrix U, a matrix sigma, and a matrix V. And here I'm going to put a star for a second. I'll talk about that in a moment. Now, the star is the Hermitian transpose. Now, if this was just a real valued matrix, this would be your standard transpose. Here I'm allowing for these matrices to be complex as well. A could be complex, but if it makes everything easier for you, you can think of these things as real valued matrices. Now, in this case, matrix V is an n by n matrix. Matrix U is an m by m matrix, right? So they are square matrices that have inherited the 2 dimensions from our original matrix A here. And the matrix sigma in the middle here fills in the gaps as an m by n matrix. But of course, I haven't really told you anything about these. I just said that you can write it in this way. For now, this is sort of just abstract nonsense. But what we do know is that U and V are orthogonal matrices. And what it means to be an orthogonal matrix, it means that our rows or columns of these matrices are orthogonal to each other. They're sort of perpendicular, okay? And that means that they are automatically invertible. And we also know that the inverse of these matrices is equal to their adjoint, okay? So here, where you see my adjoint of V, you should really be thinking about the inverse in this case. And it's from looking at that thing as an inverse that this starts to look like something you might have seen before in mathematics. And that is diagonalization of matrices, right? A is equal to PDP inverse, typically. In fact, the first fact that you can prove about the SVD is every matrix has an SVD. That is a very, very important fact that we will carry with us throughout this series. Because that means that no matter how I collect data and arrange it in a matrix, I can always apply the SVD to get this decomposition. Now, we'll talk about what the decomposition means in a moment. But the question is, how do we know this fact? In fact, it's actually very, very easy to prove. Because if we write A as this matrix right here, as this SVD, this will tell us that A times its own Hermitian adjoint, its transpose, well, this is going to be equal to U sigma squared, and then U star, or U inverse, however you would like to think about it. This is a symmetric matrix. We know that symmetric matrices are diagonalizable. And in fact, this tells us that this is the diagonalized form, P, D, P inverse. Okay? So what does this mean? It means that the vectors in U are coming from the eigenvectors of A times A transpose. Similarly, the elements of sigma is now we can see a diagonal matrix for which the squares of the elements of the diagonal are the eigenvalues of A times A transpose. Moreover, we know that symmetric matrices, their eigenvectors are orthogonal. So that's how we know that U and V are orthogonal. You can play the same trick by going in the other direction, doing A adjoint A, and this will give you V sigma squared V star. Again, eigenvalues are the diagonal entries in sigma squared. These two matrices have the same eigenvalues because they are transposes of each other. But now you can see that V is going to be the elements, the eigenvectors corresponding to this symmetric matrix. So that tells us that we can get V, we can get U, and we can get sigma. So this is, what, 3-line proof of why the SVD exists. Now, as I alluded to, sigma is diagonal in the sense that the only non-zero entries of sigma lie along its diagonal. Now, remember, it's a non-square matrix, so there could be a whole lot of zeros in here. It could be tall and skinny, it could be short and fat. But the only non-zero entries are on its diagonal, and we call these entries the singular values, okay? So I call these small sigma to denote the diagonal entries of this matrix. What I also know is that they are non-zero, that they are non-negative, pardon me. And we also organize the elements in sigma in decreasing order. So we put the largest singular value in the top left column, and then we order them as they go down. You can always achieve this just by rearranging the rows the columns in U and V. Now, what we also know is that these things will be positive for all of the i's up to the rank of A, okay? So there is only the same number of positive singular values as there is for the rank of your original matrix. Remember, the rank, that's the dimension of the column space that's spanned by the matrix. So we always order these things, sigma 1, which is greater than or equal to sigma 2, and so on and so forth. And then there is this one, the rank of A, and then everything after that is going to be 0 for greater than or equal to the rank of A plus 1. Okay, so that means that this SVD carries information about the original matrix, right? If we didn't know the rank of the original matrix, we could look at just how many positive singular values we can get out of this thing. Similarly, another thing that's very useful here is that if R is equal to the rank of A, then this dimension n, so the last n minus R columns of V span the kernel of A. Right? So again, something that you're often very interested in whenever it comes to matrices, right? The null space, the kernel, right? These are the vectors that are sort of annihilated whenever they're multiplied against this matrix A. Now, one thing that you should keep in mind is that these matrices are non-unique, right? And that just sort of comes from the fact that eigenvectors are non-unique, right? Constant multiples of eigenvectors are non-unique. What is unique, though, is the eigenvalues, right, that are captured in these singular values. So, you and I could run an algorithm and find the SVD. We might get U and V that are not exactly the same, but capture the same information, but we are always going to get the same singular values, right? So the singular values are really sort of the way of measuring information inside of the matrix A. Now, one way that I like to think about matrix decompositions here, matrix factorizations, is sort of what they represent geometrically. And so let's talk about this for a second. And so let's say the geometric interpretation. And what I want to start with is I want to start with the case where you have a diagonalizable matrix, okay? Let's not talk about the SVD for a second. Let's imagine you have a matrix and you do your sort of standard PD P inverse, right? You diagonalize it, right? So this is assuming that the matrix is actually diagonalizable, because the reason I want to start here is because these things represent very similar aspects of the geometry here, okay? So this might be something you're a little bit more familiar with from a linear algebra class. Let's start there. Okay, so I like to think of matrices as operations on vectors. So if I take a vector and I multiply it by a matrix, we can ask ourselves what this decomposition actually represents. Well, just by writing this out, we just have, this is just notation. It's just a bunch of scribbles on a board for a second. But let's take this apart piece by piece, okay? First of all, how should we interpret the first multiplication? P inverse times x. Well, the way that you should interpret this and what it's actually doing is it's introducing a change of basis into your coordinate system, okay? It is now putting you in an orthogonal coordinate system, okay? Because the p's here we're going to assume are orthogonal matrices, just like we had here. It moves you into an orthogonal coordinate system, but not your sort of standard, x, y, z plane, for example. It puts you into an orthogonal coordinate frame that is relative to the action of the matrix A, okay? So maybe it looks something like this instead, right? Instead of your standard up, down, left, right. Then, because D is a diagonal matrix, what this next action does, so first you put yourself in an orthogonal coordinate frame, then all you're doing is stretching or compressing the axes, right? So maybe this direction gets stretched and this direction gets compressed, depending on the value of D, right? That's just the eigenvector, or the eigenvalue, stretching or compressing your vector. And then what happens by multiplying the next P back into this thing is it takes you out of that orthogonal coordinate frame that you did the multiplication in, and it puts you back into the Cartesian coordinates that you started with, okay? So change of coordinates, stretch or compress, change back. Now if we think about this in the context of the SVD, let's look at this for a second. This is effectively doing the same thing, but it's doing it for non-square matrices. Remember, if you think about this as multiplying vectors, you need an n-dimensional vector multiplied in, and you get an m-dimensional vector coming out. So you're going between different spaces. But effectively the same thing is happening. This is again, think of this as V inverse. It's multiplying you through and it's changing coordinates into an orthogonal frame of reference. Then this diagonal matrix is stretching or compressing you in that orthogonal frame of reference. And then this is transforming you back out into the space that you were going into, right? So this is why I started with the diagonalization argument, because it's much easier to understand in terms of diagonalization, whereas here you're sort of moving between different spaces, so it becomes a little bit harder to do the accounting here. Now, there are many very useful pieces of the SVD that we will sort of carry with us in this lecture series. And one of them is called the reduced SVD. And what this effectively does is it allows you to sort of compress your data. Okay? So again, the way that we should be thinking about this is data stored in the matrix A. And we have this decomposition. One thing that we immediately get out of this decomposition is the rank of the data. So you can, in some sense, this functions as a dimension of the data, right? So we're going to see an example of this later on in the lecture series. But you could imagine, this data lives in maybe 100-dimensional space. That would be your M, and you have, n instantiations of it. Well, if the rank was only 2, it would tell you that you're using sort of 100 dimensions to describe something that's really only 2-dimensional. What the reduced SVD allows you to do is sort of compress the dimension of these things and get approximations in lower dimensional space. So in particular, if you pick a value, say, call it R, which is between 1 and the rank of your matrix A, what you can do is you can take this SVD, but take this, what we're going to call U sub R matrix, which is going to be an M by R matrix. And basically what it is just keeping the first R columns of U. Similarly, I'm going to take sigma R, which is going to be an R by R matrix, which is just keeping the first R columns and the first R rows, so the sort of top corner of that matrix. And I'm going to take this to be an N by R matrix, which again is just keeping the first R columns. Okay? Then what we call the reduced SVD of the matrix A, I'll call this A sub R, which is going to be UR sigma R VR star, right? And so if you picked an R that is smaller than the rank, you've effectively compressed the data, right? These matrices are smaller. That's because the R is smaller than hopefully N, because N is an upper bound for the rank of this matrix. And effectively, what you can prove with this thing is that this is a rank R matrix. Okay, so what you've done is you've picked something smaller and you've compressed the data in A into a smaller dimensional space. Remember I said the rank functions as a proxy for the dimension of your data. So therefore, you've compressed things down to rank R. You've compressed the data down to dimension R, roughly. And it turns out that the reduced SVD has a lot of powerful properties that we can carry with us as we're sort of doing data analysis. In fact, sometimes what we like to do, as I mentioned, if this is sort of a proxy for the dimension, you can look for best approximations of your data in certain dimensions. So for example, you could ask yourself, what is the argmin, so the matrix that minimizes the following problem? It is going to be, let's call this let's call it B for a second. I think that's easier. If I have the known matrix A, and I would like to get as close as possible in the Frobenius norm, such that the rank of B is equal to some number R, then we can prove, so therefore, you can prove that the absolute minimizer, the best you can do, the best rank R approximation of your matrix A is equal to that reduced SVD. right? So if you want a sort of lower dimensional approximation of the data in your matrix, the best you can do is this reduced SVD. In fact, you can go further on this, and you can quantify the error. So also, you can say how close these things are. If you asked what this given error is actually, well, this just turns out to be the leftover singular values, okay? So all it is sigma r plus 1 squared plus sigma r plus 2 squared, all the way to the end, all under the square root. So it's this sort of the Euclidean norm of the leftover singular values. Remember, the singular values are ordered from biggest to smallest. So if r is pretty large, these should be pretty small, right? But the important piece here is you're quantifying exactly what you're losing here. If this is small, you're not losing much. You can also do this in terms of other norms as well. And you could instead replace this Frobenius norm, which treats these things as a vector. You could do this in the 2 norm instead, so as an operator between Euclidean spaces, right? If I ask the same problem here, if I want to rank our approximation, it turns out that the reduced SVD is exactly the right choice. And in this case, the remainder or the error is just what the first singular value that's being left over, okay? So the purpose of all of this is to say that these reduced SVDs are the best approximators for compressing dimensions of data. And in fact, we have explicit computations for not just these 2 norms that are shown right here, but all kinds of different norms in terms of the singular values. So that means that if I know my matrix, I can execute a line of code, which I'll show you in a moment, to find the SVD. I can look at the singular values, and I can get rid of a whole bunch of information by just sort of looking at when the singular values start getting very, very small. Okay, let's take a look at an actual example that I've coded up for you here. You can get this code yourself in the link in the description, and you can go ahead and apply it to any sort of data set you want, right? You just need to sort of swap in the data matrix. So in my case, I'm going to apply this to height and weight data, and I'm going to load that data in as x. And here it is plotted for you, okay? So you have your weight. Everything is sort of normalized to have 0 average just to make the data work out better. And so essentially what you can see is a sort of general trend here, right? The higher the weight, the higher the height, right? You can see this nice sort of trend. You know, you can almost visualize a line of best fit that sort of fits through this thing. So this is going to be my data, 2-dimensional in the number of rows, and it is 200 columns, okay? So this is gathered from 200 individuals. So if you think of your SVD being applied to this, you're applying it to a 2 by 200 matrix. Okay, so then let's take a look at what we can do. Here's my SVD application. In this case, the econ is just going to get rid of a whole bunch of zeros here. I'm using MATLAB just in case you are not familiar with this. But essentially, all this is going to spit out is the 3 matrices of the SVD. U, sigma, in my case S, and V. And what we could do after we do this is print out the matrix S. Okay, so take a look at this. Diagonal, 2 by 2 matrix in this case. That's coming from the reduced SVD. They just sort of chopped off all of the rest of it, that's zeros. And you can see that one singular value is like 4, almost 5 times as large as the other singular value, right? So if we think about this from a data perspective, it means that most of the information is captured in this first singular value, okay? Think about that approximation stuff that I was showing at the end on the board here, where this sort of low rank approximation. Now let's actually see what this means in practice though. Let's take a look. Let's do the rank 1 approximation. So this is r equal to 1. All this is doing is keeping the first row and column of V and the first singular value. Okay, so I'm just multiplying it in this way. But let's take a look. Let's plot this thing, and here it is. Okay, so essentially that's the line of best fit we were just talking about. This is taking your height and weight data and projecting it into a single dimension. Okay, so every single one of these data points is projected onto this one-dimensional line. Okay, this is literally the line of best fit. Okay, and here I'm going to show you, this is sort of the visualization. Essentially, you can take a single data point and you have this orthogonal projection onto this line of best fit, which takes this point right here and gives you this one on the line. Okay, so we can also sort of take a look at the dominant directions of this thing. This is the line of best fit, the vector that's associated with it. This is the first column of that matrix U in this case. And again, you can see that this is the vector that spans that line of best fit. This is the direction of greatest spread in your data, right? And we know it's the greatest spread because it has the largest singular value associated to it. So what is this telling us? This tells us what we can see with our own eyes. It tells us that, by and large, in this data set, the taller you are, the heavier you are. Similarly, the shorter you are, the lighter you are, right? That is the general trend of the data set. It is not exactly what's happening all the time, but it is a trend. And so we can ask ourselves, what is the other direction of spread? Here, the other direction of spread is orthogonal, right? This is sort of the data coming off of that line of best fit. Remember, the SVD gives us an orthogonal coordinate system. So if one is going the line of best fit, the other one is going orthogonal to it. Here, these things are drawn proportional to, these spread directions are drawn proportional to their singular value. So the second line right here is very small for the simple reason that there's not a whole lot of spread in the second dimension in this data. Now, what we could also do is we could project this data into an orthogonal coordinate system. So you might be saying, Jason, how do you do that? Well, it just comes from the SVD. So for example, if I have a matrix A and I write it as an SVD, what I could do, U is an invertible matrix, right? And its inverse is the Hermitian adjoint. So if I multiply on the left by the inverse of this thing, I can take the data matrix A and move it and multiply it by this matrix U. And what that means is that all of the data is now in the coordinate system spanned by V, which is an orthogonal coordinate system. And essentially you're just stretching or compressing in those dimensions. And that's exactly what you're seeing in this plot now. Essentially what I've done is I put it in an orthogonal coordinate system. Most of the spread is taking place in the horizontal dimension, whereas you can see this small little yellow vector here giving you this secondary spread dimension. Now, we can do this for three-dimensional data as well. Basically sort of the same thing. Here's my 3D data. It's in an XYZ plane. You can see that there's a sort of up-down general trend to this thing. So what we're going to do is we're going to throw the SVD at this. Let's take a look at what's in that matrix S. So again, here, the first singular value, 147, it's like more than double the second singular value, which the second singular value is more than almost triple the third singular value, right? So what does this tell us? A lot of spread in the first coordinates. Still quite a bit of spread in the second coordinates, but not as much relative in the third coordinates, right? So most of the information is captured between these first two coordinates here. And so what we could do is we could look at the rank 1 approximation of this data. Again, this is your line of best fit, right? Because it's rank 1, it's one-dimensional. Let's take a look at it. you can see this is the line that sort of pierces right through your data in that general trend. This is what we saw whenever we looked at just the data cloud. You could see that up-down sort of trend here. And it's not perfectly up-down, right? It's not aligning with the z-axis. It has a nice slant to it here that we can see. And we can do the same thing, finding the second direction of spread. Here you can see now data is going into a plane by those two singular vectors, those two orthogonal vectors that are given to you from the SVD. And in this case, what I'm doing is the rank 2 approximation of the three-dimensional data. So I took three-dimensional data and I asked for the best two-dimensional approximation of it. Here, I know that the picture is getting a little bit cluttered, but this is the green data. You can see that this green data now exists in a two-dimensional plane, whereas the original black data exists on a three-dimensional plane. You can really see that plane in this image right here. And that plane is spanned by these two orthogonal vectors that come from your dominant singular value and your second singular value. And here's one other really kind of silly data set. This data set is three-dimensional, or it's in three-dimensional space, but it's just along a one-dimensional line, okay? So what we would expect from this thing is that there is only one non-negative singular value because the dimension, the rank, is essentially 1. And so let's take a look at what happens when we throw an SVD at this thing. Sorry, here we go. If I look at S, here it is, 360, 0, 0. We can see the two zeros there because the dimension of the data is effectively one-dimensional. It's all lying along a line. So there is only one singular value that matters here. So you can do your sort of approximations, but in this case, it's not all that interesting because the rank 1 approximation is the data. But now you can really see the benefit of this, right? Because you could be collecting data from a very high dimensional data set that is effectively maybe 1 or 2 or 3 dimensions, as we are going to see in the next video as an application to a dynamical systems model. But essentially what the SVD tells you is what's important in your data and what's not important. It talks about directions of greatest spread for your data, as we saw with the height and weight data. So, as I mentioned at the beginning of this lecture, the SVD is one of the most powerful tools we have in all of data analytics, right? It is something that has survived and been reinvented and reapplied year after year after year for 50, 60 years, or maybe even more. And it still has secrets to tell us about data. So in the coming lectures, we're going to explore how the SVD can be used for data science, as well as looking at methods that are sort of use the SVD as a crux, but are really sort of capturing dynamical systems analysis as well. So I'll see you all in the next video, everyone.